Welcome to The Explainer. I'm absolutely thrilled you're joining me today because, honestly, we're looking at one of the most fascinating realities in all of chemistry. It's a concept that sounds, well, almost like magic. The exact same atomic building blocks can create completely different materials simply based on how they're arranged in three-dimensional space. We're going to look closely at these structural secrets and see how the microscopic geometry of atoms dictates the physical world we interact with every single day.
Now, what's really interesting about this slide is the incredible contrast here. We've got a miner holding up an indestructible, brilliant diamond catching the light, right? But look around him. He's entirely surrounded by dark, flaky, crumbly rock. And here's the truly mind-blowing part. That dazzling, ultra-hard diamond and the dark, soft rock around him, they are made of the exact same element.
So that brings us to the great carbon paradox. I mean, how is it physically possible that an exceptionally brittle, hard diamond, literally the hardest naturally occurring mineral we know of, and the soft, slippery graphite inside your everyday pencil lead can both be 100% pure carbon? It just seems impossible that one single element can behave in two completely opposite ways.
To solve this mystery, here's our roadmap. 1. The Great Carbon Paradox. 2. Inside diamond's rigid lattice. 3. Graphite's slippery layers. 4. Comparing carbon's forms. And finally, 5. Silicon dioxide, sand's secret. Let's trace this journey from the invisible atomic level all the way up to the real world.
Okay, let's dive into this. Section 1. The Great Carbon Paradox. Same elements, different rules. To understand exactly how carbon pulls off this disappearing, reappearing act, we need to nail down two key terms. First up, allotrope. Allotropes are really just different structural forms of the exact same element in the same physical state. So diamond and graphite, both solid allotropes of carbon. The second term is giant covalent structure. Now this is absolutely crucial. We aren't talking about simple, discrete little molecules like water or carbon dioxide here. A giant covalent structure is a massive, continuous 3D network where literally billions of non-metal atoms are joined to adjacent atoms by strong covalent bonds. The actual number of atoms joined together is completely variable. It just depends on the size of the crystal you happen to be holding.
Moving right along. Section 2. Inside diamond's rigid lattice.
So, we know carbon has 4 outer shell electrons. Well, in a diamond, every single carbon atom shares those electrons to form 4 identical, extremely strong covalent bonds with 4 other carbon atoms. This forms a super rigid 3D shape known as a tetrahedral arrangement. And because every single outer electron is locked tightly into these 4 bonds, there are absolutely no freely moving particles left over to carry a charge. None. And that is the exact reason why a diamond just cannot conduct electricity.
And because of this continuous rigid 3D bonding, diamond has a staggering melting point of almost 4,000 degrees Celsius. I mean, think about what melting actually means at the atomic level for a second. To melt a diamond, you can't just separate a few stray molecules. No, you have to pump in enough massive energy to literally break apart these incredibly strong covalent bonds that are operating in 3 dimensions throughout the entire giant structure. It's a huge undertaking.
And this brilliantly illustrates how microscopic structure completely dictates macroscopic traits. Because of that incredibly tight tetrahedral atomic structure, diamond is extremely hard and dense, which makes it absolutely perfect for heavy-duty industrial drills and cutting tools. Also, it's completely insoluble in water and organic solvents. Why? Well, because there are just no possible attractions between solvent molecules and carbon atoms that could ever outweigh or pull apart the phenomenally strong covalent bonds holding those carbon atoms together.
Which brings us to Section 3. Graphite's slippery layers.
Now notice how totally different graphite is from that diamond lattice. Here, each carbon atom bonds to only 3 other carbon atoms, rather than 4. This creates these flat sheets of interconnected hexagonal rings. But wait a minute, carbon has 4 outer electrons, right? So if it's only using 3 for bonding, what happens to the 4th? Well, that one spare electron per atom becomes what we call delocalized. It's basically free to wander and move throughout the entire sheet. Which means graphite, unlike diamond, is incredibly good at conducting electricity.
Our sources offer a really perfect analogy for this. Think of graphite rather like a pack of cards. The atoms within a single sheet are held together by strong covalent bonds, kind of like the sturdy card itself. But the separate layers, they're only held together by weak intermolecular forces known as van der Waals dispersion forces. Because these forces are so incredibly weak, the sheets just slide over each other just like a deck of cards, giving graphite its lower density and, of course, its famously soft, slippery feel.
Let's summarize what this actually means for graphite out in the real world. It's soft and slippery enough to be used as pencil lead, where the layers literally rub off onto the paper as you write, or as a dry lubricant for stiff locks. And its delocalized electrons make it ideal for things like battery electrodes. But here's a fascinating point you really must remember. Despite being so soft, graphite still has a very high melting point, very similar to diamond. Why is that? Because melting it requires way more than just sliding the layers apart. You eventually have to snap those strong covalent bonds within the sheets to break down the structure entirely.
Moving on to Section 4, Comparing Carbon's Forms, the ultimate showdown. So the crucial point is, when we put them side by side like this, the cause and effect becomes crystal clear. Diamond has 4 bonds per carbon, graphite has 3. Because diamond uses all of its electrons in a rigid 3D frame, it's incredibly hard and cannot conduct electricity. Graphite, on the other hand, uses only 3 bonds, so it forms slippery layers, making it soft, and it leaves a free electron, making it conductive. Yet because they are both giant covalent networks reliant on strong carbon-to-carbon bonds, both boast incredibly high melting points. So the exact same element, with completely different properties, based entirely on geometric arrangement. It's wild.
Let's move to our final topic and see how this builds. Section 5, Silicon dioxide, sand's secret.
Enter silicon dioxide, which is commonly known as silica. You probably know this as the main chemical component of everyday sand. Now, it's not made of carbon at all, it's made of silicon and oxygen, but it takes the structural playbook of a diamond and just perfectly mimics it.
Just like diamond, silicon dioxide relies on a giant covalent network. But instead of just carbon, every single silicon atom locks into strong covalent bonds with 4 oxygen atoms, and every oxygen atom bonds to 2 silicon atoms. It literally steals diamond's structural playbook, creating a nearly identical 3D tetrahedral arrangement. And because it steals the geometry, it inherits the superpowers. It locks up all its electrons, so it can't conduct electricity, it's incredibly hard, it's totally insoluble, and it takes a massive 1700 degrees Celsius to melt it.
It really makes you look at the world differently, doesn't it? If simply rearranging atoms can turn soft pencil lead into the hardest known mineral on Earth, what other hidden superpowers are just waiting to be unlocked in the microscopic geometry of everyday materials? I want to thank you so much for joining me on this structured exploration today. Keep questioning, keep learning, and I will see you